Limits at infinity are often really well suited to using L'Hopital's rule, since if you try to Taylor expand a function about infinity, that's not going to work so well. So, let's consider some limits at infinity. Consider first the limit as x goes to infinity of log of x divided by the square root of x. This is not so obvious. Both of these functions are growing, they're going to infinity, but at relatively slow rates, and it's not clear which one is growing faster. There's no way that Taylor series is going to be helpful here. We can't Taylor expand about infinity. So, let's try using L'Hopital's rule. Taking the derivative of the numerator of the denominator, what do we get? We get the limit as x goes to infinity of, in the numerator, the derivative of log is 1 over x. In the denominator, the derivative of x to the 1/2 is 1/2 times x to the minus 1/2. Doing a little bit of algebraic simplification leads to the limit as x goes to infinity of 2 divided by square root of x. Now this is easily evaluated to be 0. Great. What about a more complicated example? Consider the limit as x goes to infinity of natural log of hyperbolic cosine of x, all divided by x minus square root of x. Okay, let's try using L'Hopital's rule. We have the limit as x goes to infinity of what? Taking the derivative of the numerator, I get 1 over cosh of x times the derivative of cosh, which is, as you recall, sinh. In the denominator, I have the derivative of x, that's 1, and then minus the derivative of square root of x, 1/2 x to the negative 1/2. Okay, now, what are we going to do? Well, in the denominator, that x to the negative 1/2, that's getting really, really small as x goes to infinity. So in that limit, I could say that denominator is going to 1. The numerator, on the other hand, is going to sinh over cosh, that's tanh. We're really just getting the limit as x goes to infinity of hyperbolic tangent, and we've been there before. This is something that we know that we can figure out, but it's not going to be amenable to L'Hopital's rule anymore. So let's go back to this problem of computing the limit as x goes to infinity of hyperbolic tangent. Recalling the definitions of sinh and cosh, and computing the limit as x goes to infinity of sinh over cosh, what do we write that out as? Doing a little bit of factoring, sinh is 1/2 times e to the x times quantity 1 minus e to the minus 2x. In the denominator, cosh is 1/2 times e to the x times quantity 1 plus e to the minus 2x. And now, canceling out that common factor of 1/2 e to the x, we're left with the limit as x goes to infinity of 1 minus e to the minus 2x divided by 1 plus e to the minus 2x. Now, both of those exponentials with the negative exponent, x is going to infinity, oh yeah, those terms are going to 0. Now, if you want to get really fancy, we could use the Taylor expansion of the exponential function, because again, that exponent is really, really small, and so we're effectively Taylor expanding about 0. That would work, but there's really no need to do any of this, because those exponential terms, they're going to 0. When we evaluate this limit, we're left with 1 over 1, the final answer, 1. I think this is kind of important. When L'Hopital's rule fails, you've got to think your way through it. So let's keep thinking. Let's think about that limit we looked at previously. The limit as x goes to infinity of log of cosh of x divided by x minus square root of x. Now, let's think in terms of factoring instead of L'Hopital's. I have the limit as x goes to infinity of what? In the denominator, I'm going to factor out an x. What's left over is quantity 1 minus x to the negative 1/2. In the numerator, we have the natural log of cosh of x, but cosh of x factors as 1/2 times e to the x times quantity 1 plus e to the minus 2x. Now what we can do is use logarithm laws to simplify that numerator. The log of the product is the sum of the logs. So we have the limit as x goes to infinity of that denominator again. In the numerator, we have log of e to the x, that's x, plus log of 1/2, that's minus log of 2, plus log of quantity 1 plus e to the minus 2x. And now if we look at the numerator, look at the denominator, there are terms in there that are definitely going to 0 as x goes to infinity. In the numerator, that e to the minus 2x, that's going to 0. In the denominator, that x to the negative 1/2, that's going to 0. Now, if you want, you can get kind of technical and we can do a Taylor expansion of log of 1 plus something, and we could do a geometric series. There's all kinds of things we could do, but look, let's just send those terms to 0 and use some limit laws. What we'll get is the limit as x goes to infinity of x minus log of 2 plus log of 1, all divided by x. Those constants are irrelevant. That limit evaluates to 1. Now again, based on what we know about the limit of tangent, we didn't need to do all this. We're kind of overthinking it, but, and this is kind of important, we're seeing the same pattern over and over again of manipulating these functions within these limits and then saying, you know what, this part doesn't matter. Ooh, this part really matters. There's something about working with these limits that is pointing towards a more general theory.